Hello, I'm Jacob Fontaine from the University of Rhode Island, and we're going to be going through my presentation of load mitigation of floating wind turbines in extreme storms through deep reinforcement learning. To give a quick overview of the presentation, we'll first go over the objective, the methodology. We'll then go into some of the software used, such as OpenFast for modeling of wind turbines and their unsteady aerodynamics, neural networks and how they work and learn, reinforcement learning inside OpenFast using the deep deterministic policy gradient, the simulated environment, the chosen reward function. We'll then go through a quick hyperparameter search and some results and analysis using pitch control and also cable control. So the objective is to develop a deep reinforcement control algorithm for mitigating tower-based moments by actively pitching individual blades in the OpenFast Simulink environment. And if you use the control mechanisms already available to every modern day turbine, such as pitch control, it could be quickly applied as a software update. So going back, we can see that the pitch right here, so the turbine tilting back around the y-axis, and also the roll, which is the turbine rotating around the x-axis. These create rotational forces on this tower base section right here, and these will be the forces that we are trying to minimize in the OpenFast simulation. So the methodology is to use MATLAB's reinforcement learning toolbox, which has access to a variety of actor and critic algorithms such as PPO, TD3, and the one we will be using today, which is the deep deterministic policy gradient. OpenFast, originally written in Fortran, is able to be run in Simulink via the fastx function available from compilation of source code. And so if we can use DDPG to interact with Simulink fast and learn an optimal control strategy to minimize tower-based moments, then we can hopefully reduce fatigue and increase the life of the system, leading to a lower levelized cost of energy. So a brief overview of OpenFast. So OpenFast is the modular computer toolbox built for designing wind turbines. It is created by the National Renewable Energy Lab and has a variety of uses such as calculating environmental loads, calculating power output, turbine deflections, so structural dynamics, and the forces at different sections of the turbine, such as shear force and moment. And we will be looking at the tower platform connection, which would be, say, around here for this turbine as well. So the aerodyne, which calculates the aerodynamic forces of the turbine, uses actuator line theory, in which forces are computed at 2D cross sections over and then integrated over the length. It also uses blade element momentum theory for coupling of the wake, but as the turbine will be fixed, we don't have to worry about this. You set individual aerofoil properties, like you can see down here, how this is discretized into a bunch of different segmented airfoils, and also tower properties and drag. For unsteady aerodynamics, it uses the Betos-Leishman unsteady model, more specifically the Minima-Pierce model for dynamic vortex forcing. So this theory is used to estimate unsteady aerodynamic coefficients based on pitch angles, static aerodynamic curves, flow speed, and it uses these unsteady coefficients in the actuator line theory. The model we will be using is the 5 megawatt OC4 floating platform. So for aerodynamics, it has unsteady flow, stalling, and dynamic vortex shedding. For the hydrodynamics, it has first and second order potential flow excitation, and also augmented potential flow with Morrison's elements to account for viscous effects, or quadratic damping matrix from CFD analysis. For the moorings, it uses Moordyne, which is a lump mass discretized catenary mooring system. For structural mechanics, it has Timoshenko beam elements, so large deflections incorporate or add a moment onto the beam as well. And it has almost full degrees of freedom, but the turbine is prevented from spinning. So for neural networks, so what is a neural network? Essentially, it is a black box that takes an input and gives you an output. It's a great universal approximator. There are more modern features such as intermediate features or saliency via occlusion that kind of transforms that black box into more of a gray box. We can't exactly know why it is making the conclusions it is. We can kind of see the process it goes through. First, how do they learn? So some important concepts are numerical differentiation, chain rule of calculus, backpropagation, gradient descent, learnable weights and biases, which is a big one, and also differentiable activation functions. So on the left here we can see the perceptron, which is kind of like the basic neuron in a neural network, and it takes its inputs, and each input is multiplied by its own weight, which then gets summed up with also the bias, put through an activation function where you get your output y. And the formula can be seen down here. So how do they learn? You first initialize weights randomly. You perform what's called the forward pass, which propagate input forwards, where the output of each neuron moves to the right in this figure until the end of the network. And a final prediction is given to the network, or a final prediction is given in the final layer. Since this answer is known, so this is a CAD, this is a supervised learning, the network compares its estimation against the known answer, and it calculates a loss based on the loss function, typically cross entropy for this case. And the goal is to minimize this loss function. Through the chain rule of calculus and backpropagation, the effect of changing each weight can be determined on the loss function, which is known as the backwards pass, and the weights are then updated with the gradient descent equation, in which these new weights equal the previous weights minus the gradient with respect to each weight times alpha, which is this learning rate. So in this figure you can see this image, 16 by 16 pixels. You take all those layers, add them up into one long column, and they are now the inputs into the network. So the strength of neural networks is in numbers. With a large amount of simple computations, neural nets can achieve great accuracy in approximating functions. On the left here we can see the multi-layer perceptron, and is considered deep with 3 or more hidden layers. As an example of a larger network, more modern, you have ImageNet, in which it combines these convolutional layers and max pooling along with these dense fully connected layers. And you can see these are kind of like Lego blocks in which you can add the different layers to accomplish which task you need in the final output. So for reinforcement learning and OpenFast. So for reinforcement learning is a method in which an agent learns how to maximize reward based on action in its environment. It's essentially smart trial and error. On the top right here, we can see that the agent is allowed to act in an environment where it receives the observations from the environment and also a reward. In our case, this agent is the MATLAB actor-critic neural net. The reward is a user-specified reward function. Its actions are individual pitch control, and its observations are tower-based moments, wind speed, and wave elevation. So the deep deterministic policy gradient is a model-free reinforcement learning method with continuous action space, which makes it different from standard deep Q learning, and discrete and continuous observational space to maximize the reward. So brief introduction to the algorithm: you initialize the critic network and the actor network. It does actions and observes what those actions do into the replay buffer. It then samples these data points denoted by your mini batch size. It calculates the loss function to update the critic weights, which it wants to minimize this loss function, which is essentially learning the transition states from one input to the next observations. And then you update the weights of the actor network by trying to maximize the reward function as shown. So the pseudocode can be seen here. Again, you initialize the critic and actor network along with these target networks. So there are 4 total networks in general. These target networks are used for learning stability. You initialize the replay buffer. And another important aspect of DDPG is this random process noise for action exploration. If you had something like a PPO, which gives you a normal distribution of actions to take, you could simply just pick different actions from that Gaussian distribution to try out and see how they do. But as this is a deterministic policy gradient, we must forcibly add noise for action exploration. You then select an action plus noise according to the current policy and exploration noise. You execute that and observe reward and a new state. It's these 4 states that go into the replay buffer and are sampled from the replay buffer based on your mini batch size. You update the critic to minimize the loss, and you update the actor to maximize the Q value. And you can also use a smoothing target factor to update these target networks as well, so they are not exact clones of the actor and critic, but they follow it closely. So reinforcement learning, its strength is in generality. So for all these examples, this is from the original Lillicrap paper. It's the same architecture, just applied to different environments and reward functions. So all of these here, it is all, so for cart, pendulum swing up, cart pole swing up, the algorithm is able to learn with the same architecture in just different environments. The environment we will be using though is this OpenFast S function here. This is the agent block with MATLAB's reinforcement learning toolbox, and it gives actions into OpenFast, which will be used in the blade pitch angle, and it receives observations where a reward is calculated, and also it just receives the full observations here. So available controls such as like torque control, yaw, blade pitch, cable control are all available right now in the fast nonlinear wind turbine S function, but there are more exciting controls coming soon, such as active tuned mass damper, active tuned liquid mass damper for active ballasting, and also just complete external forcing of the turbine platform. The reward function chosen is shown below, where M control is the normalized moment based on the observations, and M baseline is the baseline simulation run with the same environment characteristics to almost act as a noise disturbance rejection. So an issue encountered was how does the agent know it is bringing the moment back closer to zero because of its actions or the environment, such as the waves, and this was a step towards fixing that. There is also a coefficient to allow a negative reward based on large control actuations. So each of these mu are the individual blade pitch commands, and we have 3 of them. And also this observational slope was added, in which the slope from 2 consecutive observations are compared against each other, and a large variation yields a very negative reward for that situation. And moments are manually normalized by the maximum moment experienced in the baseline, so everything is between -1 and 1. For hyperparameter search, we'll be sweeping through number of layers in the actor and critic, number of neurons per layer in actor and critic, the batch size to use, and the learning rate of the actor and critic. For the test environment, we'll be using the IEC design load case 6.1, which has a hub height wind of 47.5 meters per second, a significant wave height of 10.7 meters, a peak period of 14.2 seconds, and a wave direction of 45 degrees. So for first, we can begin with a hyperparameter search of the neurons and layers. So on the top here, we can see 64 neurons and 2 hidden layers, 128 neurons and 2 hidden layers. I like the strong stable growth by the 64 neuron and 128 neuron 3 hidden layers, so they will be moving on into the future. It's also possible that the deeper networks were not given enough time to learn, but you have to eventually make a cutoff, and mine was at 300 samples for this case. So the batch size, which is examining the effects of changing how many points are sampled per episode on the overall reward, and it was for here chosen that 64 neurons and 2 hidden layers with a batch size of 128 moves on. So I'd like the final reward and also the low critic loss. And this batch size took around 24 hours, with these larger 128 and 256 batch sizes taking much longer than the previous, which was to be expected. For examining the effects of how quickly to fall down the gradient, so the learning rate of this alpha, we conducted another hyperparameter search with trying out different learning rates, and at the end it was determined that a actor learning rate of this and a critic learning rate of that was to be chosen. An important thing to notice is the batch normalization is currently unavailable in MATLAB, so I had to manually scale values from an uncontrolled run, but it has been shown that batch normalization greatly improves the DDPG algorithm when you have different physical units such as positions versus velocities, and which may range across varying environments. Here we can see the final reward or final architecture for FastNet. After the hyperparameter search, my architecture was compared against the original Lilycrap paper's architecture, and the original DDP architecture outperformed mine by a large margin. So in the end, I actually just decided to use their architecture, which consists of 500 fully connected followed by 400 in the actor, and in the critic 500 and 400 as well. This tanh layer is to squeeze the outputs between -1 and 1, and we're also scaled up by the maximum allowable user-defined pitch angle. And the overall output is the Q value. So the critic uses its weights to minimize the loss value based on what it thinks it should be, and the actor changes its weights to maximize this Q value based on its available gradients. So for some results and analysis, we'll first start off with pitch control. So the final reward of training looks as so, where we can increase from -40 to 0, and the actual estimation for what the long-term Q value should be and what it actually was dropped down significantly also. For the tower-based pitch moment, we can see that there is indeed a smaller magnitude in the pitch moments examined, but if you look at the actual control actuation, you can see that it first only does this large initial change and then very minimal control effort going on in the future. Since the roll moment wasn't included in the reward function, it saw a much larger average increase over the simulation duration when compared to this baseline. We can look at the power spectral densities of the tower-based pitch moment to examine the energy in each frequency range based on the OpenFast simulation. And so while we did have a reduction in mean pitch by roughly 8%, we had an increase in mean roll moment by 140%. And looking at the PSDs, which don't really reflect the means, we can see that even the active control had a higher power in this low frequency range and lower frequencies in some range, but not much of a large effect. Here we can see an example of the agent learning by tilting its blades in different ways and examining the observations, and also examining the reward that came with those observations. So for some results and analysis of cable control, so we have actual active control of the mooring line cables, but what it tends to do is thrust the turbine down to get the tower pitch moment below the baseline. Then it kind of struggles to deal with this reaction, and so you get this highly oscillatory going back and forth in certain areas, which will be reflected in the PSD in the future. So a lower magnitude definitely, but an increase in frequency. For the roll moment, there was no reduction in roll, but this was to be expected as this was not included in the reward function. Again, an increase in frequency of the signal can also be examined here, but it was good to see a smooth transition between different change in cable lengths. So for the PSD of the pitch moment, we can here at these higher frequencies see a much larger increase due to the oscillatory nature of the thrusting back and forth, and also just an increase in the power at these lower frequencies as well, and almost everywhere across the board, if not everywhere. So it was interesting having an agent learning in a non-linear environment. Model free is beneficial when it is difficult to incorporate dynamics into the control algorithm. It is also possible to train it experimentally instead of on software, which is another cool feature of the DDPG, as it is a continuous actor. The agent tends to learn shortcuts, so the reward function must prevent it from doing this. This was shown by the down thrusting in cable control. Its power is its ambiguity. As long as the agent can act in the environment with the control, it can learn the best actions to take. For future steps, I'd like to redo this hyperparameter search with the original Lilycrap architecture, create a better reward function. We could do this all on the University of Rhode Island's Bay Campus cluster, where each node will have a parallel running agent training on the CPU, so that's the Simulink, and the gradients on the GPUs. and also train in more environments. So if you vary the wave and wind directions, which in my opinion is essential to having this DDP agent learn an optimal control strategy, you could have it be agnostic to whatever environment it is currently in, whether it be a small storm, a large storm. It'll still know how to maximize the or minimize the tower moments. Thank you.